Okay, well, welcome to the final track 2 on algorithms and software of the conference. We've certainly saved the best for last. We have 3 very exciting presentations. First up is Michael Monagan from Simon Fraser University, and he'll be talking about speeding up polynomial GCD algorithms, which is a crucial operation in Maple. Go ahead, Michael.
So good morning from Vancouver. As Paul said, I'm giving a talk on computing polynomial greatest common divisors, which is an old problem, but it's an important one. I have 2 slides, some theory and some results. So the problem that I'm looking at is I'm given 2 polynomials. They're polynomials with integer coefficients, and I'm assuming they're in n+1 variables. I have in mind multivariate polynomials, big polynomials, sparse polynomials, and I want to compute G, which is the greatest common divisor of the input polynomials A and B. This happens every time in Maple when you simplify a fraction of 2 polynomials, or more generally a fraction of 2 formulas. Maple computes the greatest common divisor G, and it's going to output the simplified fraction. I'm labeling it A bar over B bar, which you get by dividing the numerator A by G and B by G. Maple has had polynomial greatest common divisor code since its very beginning. In 2005, Maple started using Zippel's sparse GCD algorithm. And I just want to give you an outline of Zippel's sparse GCD algorithm. Our algorithm, the one I'm presenting, is very similar. So both of the algorithms, they work, at least the first step is the same way. We compute the GCD modulo a sequence of primes. And then we apply the Chinese remainder theorem to reconstruct the integer coefficients of the GCD. The 2 algorithms differ in how they do the hard part, which is how do you compute the GCD modulo the first prime. And this is how they both work. They both pick an evaluation point at random, and then they compute images of the GCD. So they compute an image, GJ, which is you evaluate both polynomials at all variables except 1. So you evaluate x1 at alpha 1 to the j, x2 at alpha 2 to the j, etc. Same for b. And this means you have 2 polynomials and 1 variable left. Then we compute the GCD of those 2 polynomials using the ordinary Euclidean algorithm. And then the job is to interpolate our GCD, the multivariate polynomial, using these images that we have, using sparse polynomial interpolation. And the algorithms differ in 2 ways. They differ in how they do the sparse polynomial interpolation and the choice for the alphas, how they choose the alphas. I've said they choose them at random here. Our algorithm is not exactly that, but it's still random. Here's a theoretical comparison showing how much faster the new algorithm is in theory than the old one. So I have 2 parameters. D is just the sum of the degrees of the GCD-G, adding the degrees in every variable. And T is the number of terms of the GCD. So with those 2 parameters, Zippel's algorithm needs of order D times T images, and it also solves some linear systems. It has to do solve order D linear systems. Our algorithm, Lucas Hu was one of my PhD students, and we published the first version of the algorithm in 2016, and we published a more complete version and a journal paper this year. The new algorithm does only order T. It needs only order T images, and it does 1 linear solve. So you can see that it's a factor of order D times faster. So it should be faster. If the polynomials have many variables or they have high degrees, D would be large. So here's some data comparing the new algorithm with the old one. So I've got up the top that I've implemented our algorithm. I've implemented it in Maple, and I have coded some of the subroutines in C, some of the substeps in C for efficiency. And what you see in this table is timings comparing Maple. So GCD is Maple's time for computing the GCD. MGCD1 is the implementation of our algorithm. And then since I implemented it, I saw something and I've made an improvement, a significant improvement. So the best timings are in this column. In the table, there are two sets of timings. In the first set of timings, the inputs A and B have 100,000 terms. In the second set of timings, they have 1,000,000 terms. Now I constructed the inputs as follows. I constructed G, it's a polynomial in 8 variables with degrees up to 30. So I just chose it at random, coefficients 100 bits long. Same for the A bar polynomial. So I have 2 random polynomials. I multiply them together to get A, do the same for B, and I've got a GCD problem. What you see in the table is 2 sets of timings. In the first set, I have the size of the GCD increasing from 10, 100, 1,000, 10,000 terms. And so that the inputs have the same number of terms, the A bar and B polynomials, they are decreasing in size. So I have a family of GCD problems from what I would call a small GCD up to a big one. And what you see in the timings is that for Maple's algorithm, the timings increase simply because we have to interpolate a bigger object. G is getting bigger. It needs more images to interpolate, so the time goes up. Goes up sort of roughly by a factor of 10. It's approximately linear increase in cost. Same happens for our algorithm. So you can see that our algorithm really is quite a bit faster. Comparing this time here with this one here, it's over a factor of 200 times faster. So that's a very good improvement. I noticed something though, that the time does increase in the next batch of timings. You see that it starts at 7 seconds and it goes up to 3,500. And so I thought, okay, I need to think about how to improve this. What I've decided to do is to try to interpolate the smaller of G, A bar, and B bar. So I'm going to interpolate them simultaneously, but I'll stop when I get the smallest one. And that can be done. I've worked out the details. The algorithms are probabilistic, so I need to be careful about some of the details. And what you see in comparing these timings here with the ones on the right is that the time on the right increases, but then as the cofactor, well, the A bar and B bar polynomials are smaller, it starts interpolating them, and you see the time go back down. So my best time in this set of timings is this one, 11,000 seconds reduced down to 1.45 seconds. It's almost a factor of 10,000. It probably would be a factor of more than 10,000 if I could wait for Maple to finish here. Okay, so that's the results, and I'm going to stop the talk here and take questions.
These are fantastic timings, especially for such a core algorithm.
Thanks, Paul.
Yeah.
It's almost a 10-year research effort because the first effort was a flop. We messed it up.
Getting a 10% speed up is often very satisfying, but getting 10,000 is unheard of. So for the audience, if you have any questions, please use the Q&A box and type them in. I do see we have some in the chat.
Can you read them out? Because
so Rob just makes a comment. It probably would have been bigger than a factor of 10,000 if I could wait for Maple to finish.
Yeah, exactly. So maybe I should just run it and wait for Maple to finish. But they are going up by a factor of 10, right? This is in principle a factor of 10, so it becomes 300,000. So and it uses quite a bit of space. Maple's implementation of Zippel's algorithm is using it's solving linear systems using a cubic solver and a solver that uses quadratic space. So actually, one of the other improvements I made in the implementation was to use the Zippel's fast van der Waals solver, and that got the time down to quadratic time linear space for the solve.
So you mentioned you interpolate the smallest of G, A bar and B bar. Is that done in parallel?
No, not in parallel.
Okay, so you figure out which one is smallest, and then
I just coded it. It's natural to code them together because A bar is A over G. So I compute all the images. I compute the image of G, the image of A bar, and the image of B bar, and then just interpolate all three. Start interpolating all three, and I'm waiting until I have enough points to get the answer. I'm interpolating it incrementally.
Okay. One more question from the audience. The statement is, one core assumption is that the answer is sparse. Must the degrees in each variable be sort of comparable as well?
No, it should do well. If the polynomial is dense, it still needs linear work. So it's essentially optimal, right? Because this is the size, what's the number of terms in the output in either the smaller of G, A bar, and B bar. So even if it's dense, it should be okay. And it doesn't really depend on the degrees. If some are big and some are small, that's fine. There is a little bit of a catch. The size of the prime that I need, I'm using a Kronecker substitution, so I have to pack an encoding of all the variables into one variable, into one variable. So the size of the prime is a bit bigger than needed in Zippel's algorithm.
Okay, there are more questions, but we are out of time for this part, but we'll have time at the end of the 3 sessions to come back and ask more questions. So we'll move on to the next presentation.
Gould. The timings are decreasing because A bar and B bar over here, they are getting smaller. That's why the timings start to decrease. Thank you.
Okay, thank you, Mike. Next up is Veronika Pillwein, and she's going to talk about computing a difference equation satisfied by the Stieltjes transform of a sequence.
Okay, thank you. Hi, everyone. What I'm talking about today is joint work with Diego Dominici. And in this short presentation, I'm actually not really talking about Stieltjes transform, but about this transformation that we are doing. And I'm starting out with the known thing that we are doing for this, whatever Stieltjes transform is. Namely, if you think of holonomic functions that I think most people are familiar with. So if you have a generating function f of x or a sequence an, then they are called holonomic if they satisfy a linear equation, difference or differential equation with polynomial coefficients. And it's well known that the sequence is holonomic if and only if the generating function is holonomic and vice versa. And one can compute one representation, so this equation from the other. So one can go back and forth between those two. And there are many other things known about holonomic sequences and functions, about summation and integration and closure properties. And all this is algorithmic and it has been implemented in several computer algebra systems, like in Maple, Mathematica, or Sage, to name a few that I'm familiar with. And now we are looking at something similar, but with a different type of generating function, if you will. And the application comes from the constant context of orthogonal polynomials. So I'm introducing the notions from there briefly. So the moment functional, if I'm giving a polynomial basis, Qn, so for each n, the degree of Qn is n, and it has leading coefficient 1, and a sequence of numbers, then the linear functional that assigns to each of these Qn a number mu n is called the moment functional defined by these two sequences. And if I have a family of polynomials that when I apply this to the product is non-zero only if n is equal to m, then this sequence of polynomials is called orthogonal with respect to this moment function. Okay. So, and the application that we have in mind is really for discrete semi-classical orthogonal polynomials. So these moment functions can look very complicated, don't have a closed form, but we are thinking of something that has a weight function. It's a discrete polynomial. So we have a sum here. This is the polynomial, and the weight function looks like this with this Pochhammer or rising factorials here. So if I think of q equal to 1, then what I have here is just a generalized hypergeometric function. And a simple example of the Charlier polynomials. So here this whole thing is 1, and I only end up with this width. Okay, so now the Stieltjes transform, but without context. So now I'm using phi n for the falling factorials for, say, historic reasons. So it's defined as this. So we are looking at the generating function as a formal object, where in the numerator we have the moments of the falling factorials, and here in the denominator we have phi n plus 1. So again, this falling factorial basis. And then we consider this sequence operator. So in general, we could have any sequence here, but if we plug in the moments of the falling factorials, then we end up with this S of t up there. And then we say we are given a recurrence relation for these moments, and we want to automatically compute the difference equation satisfied by this S of t, by this generating function. And in the first step, this is an inhomogeneous with a polynomial right-hand side. And of course, one can compute from this a homogeneous one if one would want to. And this name here is somehow in this in the packages that I mentioned earlier that have been developed at the risk combinatorics group. There's a recurrence equation to differential equation, RE to DE for this direction. In our case, it's a recurrence equation to difference equation, if you will. Good. So all that you need to do this is to figure out how to translate monomials times shifts into actions on monomials times shifts on this generating function. And the translation looks like this. So I'm just giving the formula here without any derivation to see how it looks like. So we have a closed form. It involves the Stirling numbers and the rising factorials again. And this part somehow in the end goes into the right-hand side in this inhomogeneity, and this gives the recurrence relation. And this is very easily implemented in any computer algebra system. And then given difference equations for moments that are known, one can automatically compute the difference equation for the Stieltjes transforms. It look like this. And here you see is the very simple inhomogeneous right-hand side. The most complicated, I think, that we have in this context right now, that we have computed is this generalized hand polynomials of type 2. So this has a second order recurrence, and we end up with this difference equation. And that's all. Thank you.
Great. Thank you very much. Again, if you want to use the Q&A panel, you can ask questions in the audience. Just a question, what role did Maple play in your research here?
So as a matter of history, I'm more used to using these packages that we develop in Mathematica. But my co-writer, so Diego Dominici, is more used to using Maple. So we have implementation in both computer algebra systems to compare with. So this is how Maple entered. And of course, this is something that is independent of the platform where you implement it, really.
You know, it's not a bad way to do things, to use multiple platforms and compare. Actually, since you have that unique experience of being able to compare the systems, is there any insight there, or how did that go?
So I I think for this, really, this is something that works really on any system very easily, because this is one of the most basic things. So if we continue this work in the future, we will start exploring more, which, if there is a preference of one over the other. At the moment, I think this is easy enough to be feasible for both systems equally. So, yeah.
Okay. A question from the audience. Someone asks that they don't know the history of the Stieltjes transform. Can you give a reference or put it in historical perspective?
So the so the Stieltjes transform. So it's a transformation of 1 over t minus x, where it acts on, say, the x on one of the variables, and you use the moment functional applied to this 1 over t minus x. You formally expand it as the geometric series, essentially, and then apply it to this object. So this is how it would be defined, really. And the historical.
Is there an application area where would you want to use this type of transform for what kind of problems?
So this is something that honestly, I know that it's being used here and it's being used in many other places, but I don't dare to blurt out say anything wrong right now.
Okay. Okay, we're at the end of our 10-minute segment. So we'll move on to the next and final talk of this section. So Anthony Ripa from Stony Brook University is going to talk about Leibniz, his software for a generics-based expression simplifier.
Sorry, I think he's going to talk about Leibniz.
Yes, of course, Leibniz. It could be like LaTeX versus latex. Go ahead, Anthony.
Thank you. Okay. Thank you all for coming to my talk. Leibniz, a generics-based expression simplifier. My name is Anthony John Ripa from Stony Brook University's Computer Science Department. Expression simplification can be thought of as coming in 2 flavors: algebra, which may produce removable discontinuities, and calculus, which may remove those discontinuities. Instead of having 2 different approaches to be used in 2 different places, we seek a unified approach. We introduce a new primitive called a generic. We use generics where we would otherwise use variables. If x is a variable, we saw that x over x was piecewise. If x is a generic, x over x just simplifies to 1. Instead of algebra creating removable discontinuities, followed by calculus promptly removing them, with the appropriate primitive, we simply avoid creating the removable discontinuities altogether. This makes problems easier to solve because the primitive is simpler and avoids needing to treat burdensome edge cases separately. Prior work implementations include the inconsistent results of computer algebra systems, such as Maple. What does Maple simplify 1 plus h minus 1 over h to? The answer is 1, even when evaluated at h equals 0. But Maple is not consistent. If I enter 1 plus h squared minus 1 squared over h at h equals 0, Maple errors out. Implementation. Leibniz is a rule system for expression simplification written in Prolog. Leibniz is named after Gottfried Wilhelm Leibniz, one of the inventors of calculus, who used algebraic notation for his calculus. The pivotal rules are: simp of 0 over 0 is fail. Simp of x over x is 1. If 0 over 0 is encountered, then this branch fails. If x over x is encountered, then replace it with 1. We retry the previous problems in Leibniz. As we can see in the figure, Leibniz correctly handles both traditionally indeterminate forms. Confluence, also known as the Church-Rosser property, means that if A reduces to both B and C, then both B and C reduce to some D. This formalizes a notion of path independence. Confluence has been considered the default desirable property, so that when systems appear to violate confluence, rather than working with non-confluent systems, the original expression is labeled undefined. For example, h over h at 0 is undefined to preserve confluence. Calculus is overcomplicated because of the high price paid to preserve confluence. Relaxing confluence allows algebra to inexpensively solve what would otherwise be calculus problems. Confluence guarantees, among other things, that leaves will be equal. For example, we won't get 1 equals 2. In place of confluence, we seek a guarantee compatible with more use cases. The property, called lossless, will guarantee that no solutions are lost. The correct answer will belong to the intersection of all reductions. For example, 0 over 0 has extra solutions, but includes the correct solution. Generics have a well-defined division operator. X over x equals 1. Generic expressions that involve only the operators plus, minus, times, divide yield reduction graphs that are confluent, therefore lossless. Generic expressions that include an evaluation operator yield reduction graphs that are not confluent, but are lossless. As generic expressions always yield lossless reduction graphs, we offer methods for lossless graphs. Lossless meant that solutions are not lost. The naive approach is merely to intersect all solutions. The solutions to 0 over 0 is the universe. The solutions to 1 is 1. The intersection is 1. This approach may be expensive, but its correctness follows immediately from the definition of lossless. Backtracking arises in numerical stability. If an approach becomes numerically unstable, you may backtrack and apply a more stable approach. To simplify h over h at 0, the left branch yields 0 over 0. Confluence would imply the original expression was undefined. However, lossless concludes this particular test is inconclusive, so backtrack and try a different path. Simplifying division first, I get 1 at 0. Continuing, I get 1. In fields of active research like linear algebra, numerical stability abandoned embracing inconclusive tests in favor of backtracking, while supposedly completed fields like elementary algebra did not, inviting calculus to make up for its shortcomings. We may use numerical stability and backtracking in elementary algebra, just like linear algebra. This is better than hidden numerical stability and backtracking found in calculus laws like L'Hopital's rule and limit laws in general. In light of generics, we re-examine limit laws with an example. The limit as h goes to 0 of h over h. We tentatively distribute the limit operator over the division operator. We take the limit of top and bottom yielding 0 over 0. We conclude the conditional equality is false. We start over. We divide h by h, yielding a limit of 1. Finally, the limit of 1 is 1. Limits are a way to simulate backtracking while remaining confluent in name only. This code is available on GitHub. From there you can run the code directly in the browser. You can recreate the examples that we went over, or try more complicated examples, like this one. Thank you for your time.
Great, Tony, thank you for this presentation. Very thought-provoking. We had a preview of some of the Q&A in one of the earlier lounge sessions. So I'm sure this will spark a lot of conversation. One question from the audience, does Leibniz simplify a fraction of polynomials automatically to try and see if a over b equals 1?
Yes.
So the rule is to simplify first, factor and whatnot, before performing any operations.
Right. I think I have like a few different evaluation strategies. Let's see here. So intersecting all the solutions, that's one evaluation strategy that you could do. Just do the entire tree. Another strategy is to selectively search through the tree, and if you get 0 over 0, you backtrack. And another one is just rule ordering, where you just simplify the inside first before you apply the evaluation operator. And the 3 different approaches might be appropriate for different cases, depending on what you value, speed or whatnot.
Another question, do you have a multivariate GCD implementation?
I guess I can ask that one live, right? I forget that I'm a panelist.
I suppose you're allowed, yeah.
So, Anthony, if you have a polynomial in more than one variable over another polynomial in more than one variable, and they happen to simplify to, say, a constant like 3, will you find it?
Yeah, I think this is that example, like the x plus h squared minus x squared over h at h equals 0. So this is a multivariate polynomial, and you evaluate it and you get 2x. And if the answer happened to be 3, you would get 3.
Yeah, but how are you doing this? Are you expanding the numerator? What are you doing?
Expanding the numerator.
Okay.
So I have a question, if I may. So we talked about this before. So how do you handle sine x over x?
Right. So I guess there's a few different ways to look at this. Like, so one of this, since this is a generic data type, it's like a complex number. In some sense, it handles some situations well and others less well. So right now, it's basically doing like the finite closure of x over the arithmetic operators.
So that basically means that you have quotients of polynomials.
Yes, that's a good way to say it.
Yeah. But for that, as Mike points out, the question is easy to decide by doing greatest common divisors.
Right. And so if I were to maybe extend this beyond finite, I could do sine of x just as like an infinite sum in some sense, which right now it does not do.
But then you have convergence questions.
Yes. Yeah, right. So there would be issues if this were to be extended. I think it wouldn't be an issue in the sine x over x case, but it could be an issue in other cases.
So in Maple, don't we get this if we automatically simplify fractions as much as possible?
Yeah, you would always have to do normal, yes. But you don't want to do that, because if you have x minus 1 to the 1000 divided by x minus 1, you don't want to cancel that. Sorry, x minus 1, sorry.
X to the
1000 minus 1 divided by x minus 1. You don't want to cancel that because you get 1000 terms.
Yeah, so here's an example, like h plus 1 to the 7th over h plus 1 to the 5th, you get h plus 1 squared.
No, that's not what we're asking. You're asking h to the 7 minus 1 divided by h minus 1.
Okay, sorry, I misheard the question.
And then take 1000 instead of the 7.
Right, so it in h to the 7th minus, so I would assume this would be good for Euclid's algorithm would be good for this, I assume.
Well, this is a binomial, it's a binomial theorem, so you know what the answer is. It's not a binomial, it's a truncated geometric series. So the answer, when you take x to the n minus 1 divided by x minus 1, is 1 plus x squared plus x cubed plus x to the 4 plus x to the 5 and so on, plus x to the n minus 1. So you get a really, 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 really long expression.
Right. So in a formal system like this, I think if you didn't know all the exceptions, you might use something like Euclid's algorithm. And if you did know all the exceptions,
Euclid's algorithm, I'm telling you what the answer is. The answer is a polynomial with 1000 terms, and that is the reason why we're not doing this automatically, because it blows up the expression size.
Right. Okay. Right. So this is one of the reasons why I said backtracking is a good idea. So you want to explore some branches and you want to reject some branches.
Well, this branch is too expensive to explore, because if you would explore it, you would get an intermediate expression which has 1,000 terms.
Oh, okay. Well, then you can stop after like, I don't know, 10 microseconds and say, you know what, I'm done with this branch.
So at this point, thank you for this discussion. It was really great. We can continue it, but I would also like to open the field of questions to the rest of the panelists, since this is the conclusion of the 3 sessions in this track. So if we have more questions for Anthony, that's great. Otherwise, we will also accept questions for Veronika and Mike Monagan.
Shall I stop sharing or continue sharing, or?
Let's see what the next question is.
Very good.
So I guess, Anthony, your software is built in a prototype that you have available on GitHub.
Yes.
How complete is that, and where would you like to go with that software?
I guess maybe the next thing I was seriously considering tackling was something like sine x over x. So I guess right now it just handles the rationals, as I said, and that would be where I think I might want to go with it.
Okay.
Yeah, I have a question for Anthony too. I think you said you implemented it in Python. Is that correct?
Prolog?
Prolog, in Prolog.
Mm-hmm.
Prolog. Why did you choose Prolog? Because of the backtracking? Why did you choose Prolog?
Yeah, the backtracking was the reason. Also around the same thought was it kind of already has the idea of terms kind of. I would say backtracking was maybe a little bit more in my mind, but the terms was also there for me.
Okay, we have a question in the Q&A chat. Anthony, would you explore branches? So would explore branches make the algorithm exponential? So I think this is referring to backtracking and going through the tree of different possibilities. Is that an exponential algorithm, and is it going to be very costly to do that?
So I think you get a branch every time you do an evaluation. So I would say I don't think it's exponential, but right off the top of my head, I can't guarantee it.
Okay. We have another question, this one for Mike Monagan.
Yeah, can I share my screen again and just to show the formula, the
sure.
Evaluation?
Yeah. I guess you can see it in the chat, so go ahead.
So there is really no problem with conditioning, because the polynomials have integer coefficients. That's where I'm starting, and I'm working mod some primes, and so everything's over a finite field. And so when I go to evaluate, I'm evaluating at points over a finite field, so the computations are exact. The prime that I choose, I would like to be a machine prime, small enough so that the arithmetic can be done directly on the hardware, but it doesn't have to be. But it's over a finite field. The conditioning question would come up if we were not starting over the integers, if we were starting with a GCD problem with floating point coefficients. Then one would have to do something else. So.
All right, thank you, Mike. With that, and we've hit the noon hour, I would like to thank all of the presenters for this session and for the conference in general. This happens to be the last session. So I just want to point out that in this conference, we had 54 contributed talks, 3 keynotes, 2 discussion panels, 1 fantastic art gallery, and over 400 active attendees. And I think it was at least twice that for registered attendees. I just want to remind everyone that the recorded sessions will still be available in the theater if you want to come back anytime within the next year. So you can come back and watch the rest of the presentations. So this was a fantastic conference, and again, I would like to thank everyone for participating. And with that, we will close the session and the conference. Thank you, everyone.